pleasure to invite you to the third lecture in the series that we have on science and society, Anusandhan in a Samaj Vikas, sir. And I'm really delighted to welcome Dr. Krishnan Raghavan. So Dr. Krishnan is a climatologist. He has been modeling the climate to understand scientific issues related to climate change, Asian monsoons, and the water cycle. He has led major studies and development of the first Earth system model that contributed to the international models, IPCC and CMIP6. And he was also responsible for the assessment of the water cycle here in the country. So I can go on and on. I mean, he's been a major scientific force in understanding climate change, and as most of us realize, that's an amazingly important topic and concern for humanity, where scientists could and should make a big difference by understanding our changing climates. So Dr. Krishnan, of course, is a fellow of all the academies in India, and apart from that, he has been recognized by many awards and recognitions elsewhere in the world. I won't really spend too much time saying that, but I must say that I'm really delighted. He happy to he has come for some work here, and he agreed to come and give a talk. And so, Dr. Krishnan.
First of all, good morning to all of you. I'm sorry for the slight delay. Got held up with the traffic. My sincere apologies. First of all, I want to take this opportunity to thank Professor Tarun Saurodeep, Director RRI, for this invitation. It's really a great honor for me to be talking to you at RRI, very renowned institution. And so today, this talk on this Anusandhan in a Samajik Vikas, development of society through research. So when this was told to me, I was thinking, what is the best way I can give this talk? Not to be too technical about my own work and so on. At the same time, highlight what are the important topics. And recently, your director was there at IITM, and also Dr. Angarajan had visited one of your colleagues. So we are having this mission Monsoon, and we had some discussion about measuring profiles of water vapor and temperature in the Himalayan region. That was one of the things we thought why it's important. So I thought I will use that opportunity, build the narrative around climate change is happening, global warming is there right now. Last year we exceeded 1.5 degrees, and we know it's because of the human influence, mainly because of the greenhouse gases like carbon dioxide, methane, and nitrous oxide. And of course aerosol emissions, mostly particulate matter, they have tried to cool the planet so far. But these greenhouse gases are having a longer lifetime. They are going to stay there for coming century. So the planet is going to warm. So, and I'll briefly touch upon, so in 2021, the last IPCC report came out, in which I was one of the coordinating lead authors from India. I'll describe briefly about that. And also another remarkable thing that happened in 2021 was the Nobel Prize in Physics that was given to Professor Sukuro Manabe. We call him as Suki Manabe, who pioneered climate modeling and the studies of global warming. And I was fortunate to be associated with him. I worked with him for 2 years. I'll show some slides. So his work basically showed why the troposphere should warm and why the stratosphere should cool, much above the troposphere, in response to the global increases in the atmospheric carbon dioxide. And I will also talk about the IPCC, some projections, extreme precipitation, and briefly touch upon weather and climate models. Then what is going to happen to our monsoon? I think that's something very important for us. And how regionally, because we have the Himalayas and the Tibetan Plateau, the Indian Ocean, this very unique geography. The Indian monsoon is one of the strongest monsoons across the globe. There are other regional monsoons, but this is the strongest. And now extreme precipitation is happening everywhere. And we have these low pressure systems typically during the June to September months. They form in the Bay of Bengal and they move as they are either low pressure systems or depressions. They move west-northwest. And they produce a lot of rainfall over India. And they are getting intense, they are becoming stronger. I'll give you some examples. So making these measurements of continuous measurements of this water vapor and temperatures, they're important for research, but are also for prediction and enhancing our early warning system. So with these thoughts, this is how I've planned my talk. Please let me know in case there are not clear in some place. So basically I wanted to say it is advancing our predictive understanding, because Manabe always said we have to understand what is that phenomena, but at the same time there is a need to predict them. So it is, I said, there's a new terminology, say predictive understanding of the extreme rainfall, extreme monsoon rainfall, and I will focus on the Indian region, but also in the Himalayan region in a warming world, and how we can contribute to the society through research. So this was I'll show some slides. These are the latest temperatures, global mean temperatures, average over the entire globe. And you can see in 2024, we crossed the 1.5. It was 1.54. And so people were thinking this may happen in 2030s, but it has happened much earlier. So global warming is happening. And thanks to this carbon dioxide concentration, it is all in parts per million. It's a well-mixed gas, greenhouse gas. We have crossed 424 parts per million by volume, and since the pre-industrial times. And these are all some very strong statements from the IPCC that human influence has warmed this climate at a rate that is unprecedented in at least the last 2,000 years. And these are all based on multiple models, what are known as climate models or Earth system models. And we have our own model also from India, from our institute. And this is the observed warming that we see since 1850. It's a very rapid, at a very fast rate, the temperature has increased in recent times. And this is what this black line is the observation. And these are from the multi-models. When you have both these effects of, because temperature variations can occur also due to natural processes, natural forcings. So these are the simulations, the red line, which have both the human influence, that is the greenhouse gases, also aerosols and land use change and so on. So they are able to pretty much get this observed trend. And if you had only natural forcing like solar irradiance changes or the volcanic eruptions, they try to cool. This is the famous Pinatubo that happened. So you can get some cooling, but that is for a very short-lived period, but you don't get this warming trend. So it's the increase in the temp. Yes, sure. You mean the previous one? So this is coming because of the interhemispheric difference between the northern hemisphere and the southern hemisphere. You have more land, so there is more biosphere. So a lot of carbon dioxide is used by the vegetation in the northern hemisphere. So there is a seasonal cycle. So the carbon dioxide emissions in the atmosphere are less during the northern summer, and because there is a lot of vegetation. So because of the seasonal cycle, you get this fluctuation, and that's typically about 4 parts per million. But this increase that we see, pre-industrial value was something like 270 parts per million by volume, and now it is 424. Almost it's so it is about 40% we have added more. And so these are the seasonal variations, because that's mainly the biosphere that's controlling. Yeah, and yeah. So the main point is, in addition to greenhouse gases, there are also, as I said, there are other like sulfur dioxide and other aerosols, suspended particles, which actually reflect back and scatter the incoming solar radiation. The carbon dioxide, greenhouse gases, they mainly absorb the long wave infrared radiation radiated by the Earth. And these are mainly scatterers like sulfur dioxide. Also, when these big volcanic eruptions happen, so they go into the stratosphere. These are the ones that I showed you. The sulfates and nitrates, they can go into the stratosphere where they can stay for a couple of years. And so they reduce the incoming, they block the incoming solar radiation, produce some cooling. So when we say aerosol, we have to think mainly it is the short wave radiation, incoming solar radiation. When we are talking about the greenhouse gases, it is mostly the absorption of the infrared radiation, long wave radiation by the Earth. So what it says is, if we did not have the aerosols, the warming we would have already exceeded during 2010 to 2019 compared to, we would have already crossed 1.5 degrees. So they have produced some cooling of about 0.4 degrees. That is the main message. Yes, yeah. Sources, different sources are there. Yeah. Yeah. So
really take out the aerosol, we should also take out the carbon production associated with the...
Yeah, see, you're right. There are, as you said, there are carbonaceous aerosols, there are non-carbonaceous aerosols. The carbonaceous aerosols mainly, the aerosols are mostly in the lower troposphere, near close to the surface, maybe up to 2-3 kilometers above the surface. And so when they absorb the incoming solar radiation, there is some warming in the atmosphere. But the radiation reaching the ground reduces. The surface still cools. There is some warming. And also spatially, the distribution of aerosol, there is a lot of variation both in spatially and temporally. And so that is why the net effect is the cooling at the surface itself. So they can produce some warming in the atmosphere, especially in the lower and the middle atmosphere. They can stabilize the circulation and so on. But greenhouse gases have a much longer lifetime. And so I can discuss with you more about that, definitely. Yeah. And so this is the famous, the 2021 Nobel Prize went to these three gentlemen, Professor Suki Manabe, Klaus Hasselmann. Their contribution was for the physical modeling of the Earth's climate, quantifying variability, and reliably predicting global warming. And the third one, it was also shared by Giorgio Parisi for the discovery of interplay of disorder and fluctuations in physical systems from atomic to planetary scales. I'll just focus on this for the climate part. Basically, Manabe's model, Manabe and Weatherall, 1967, they developed a simple one-dimensional model of the atmosphere, a radiative convective model, where you have the incoming solar radiation. There is albedo about 0.3, basically, that reflects that's the fraction of radiation that is reflected. About 70% of the incoming radiation passes through the atmosphere. It heats the land, and the land radiates in the infrared radiation, which is absorbed by this water vapor and greenhouse gases. And some of it re-radiates back towards the Earth's surface and leads to the surface warming. They also considered the effect of convection. So it is radiation, not only radiation, but also convection, where they considered the vertical movement of air. So when the air, due to convection, when the hot air rises, it also carries the water vapor. And water vapor is also a powerful greenhouse gas. And that further amplifies the warming. And so with this model, he also had a simple experiment. I will show that in my subsequent slide that, so when he doubled the carbon dioxide in the atmosphere, he predicted that the warming would be about 2.3. This was in 1967, where we considered the water vapor feedback. And later on, models were refined. This was a simple one-dimensional model, radiative convective model. Later on, people developed the general circulation models, how the heat is transported, and they considered not only the atmosphere, but also the ocean, and fully coupled models. And now all these models are contributing to the IPCC, and there are about 50 odd models that have participated in the last assessment. And so how to fingerprint, how to detect the externally force that is due to the anthropogenic forcing, human-induced forcing, versus the natural variability. How do you fingerprint? That was the work of Hasselmann. And so let me not go into this detail. And so this was one of the most important paper, and this is Professor Suki Manabe in his early period, 1972. And this is Jos Megaransky, the first director of GFDL. And this was the paper, the thermal equilibrium of an atmosphere with a given distribution of relative humidity, that was awarded the Nobel Prize. And what they argued was, they had one experiment in this model where they considered this is the, if you had a carbon dioxide concentration of 150 parts per million by volume, this is 300 and this is 600. So they noted that the surface, the troposphere would warm. In the troposphere, the temperature decreases with height, and this is your tropopause. So in the stratosphere, the temperature decreases with height. Here it decreases with height, here the temperature increases with height in the stratosphere. But when you increase the carbon dioxide concentration, you find that the troposphere and the surface warms, whereas the stratosphere cools. So it's like, so when you have the convection, basically you need the vertical gradient. So it should be heated from below and you should have cooling above. So this vertical gradient in the temperature, so once, that is important for the convection. So once you're increasing that, your extreme precipitation event is going to increase. So this was this, so I just thought I'll share these slides. And he always focused on, Manabe is to emphasize on understanding the problem. And that was his, and this was the famous paper. So they consider, they said they fixed the relative humidity. They said, how do you, when you consider thermal equilibrium or radiative convective equilibrium, he fixed the distribution of relative humidity. This was a very, very important assumption or approximation that he made. And with this, so he told that the results showed that it almost, takes almost twice as long as to reach the state of radiative convective equilibrium for atmosphere for a given distribution of relative humidity than for the atmosphere with a given distribution of absolute humidity. Absolute humidity depends on the volume, but relative humidity is temperature dependent. And that they recognized very early. And also they argued that the surface equilibrium temperature of the former, that is with a fixed relative humidity, is almost twice as sensitive as to change in various factors due to the adjustment of water vapor content to the temperature variation of the atmosphere. So I'm not going to the details. And so this was my association with him. I worked for 2 years at the Frontier Research System for Global Change. He was our program director, and later I also visited him in Princeton. So in Manabe's model, this is just the electromagnetic spectrum. We have the visible radiation, the incoming solar radiation, and this is the outgoing long wave infrared radiation. You can see he considered, I'm just highlighting 4 main absorbers. One is the ozone at about, it's about 9 microns. And he also had in his model, there's absorption about 15 microns where you have both carbon dioxide and water vapor, 2 absorption bands. And with the simple four model, it's a very, very simplified radiative convective model. He predicted that due to the water vapor feedback, so by doubling the carbon dioxide, the planet would warm by 2.3, which is almost quite, it's coming close with now what the present state-of-the-art models are predicting. So this is the change in the radiative forcing. So we have various greenhouse gases like carbon dioxide, methane, and other halogens, nitrous oxide halogens, also ozone. And there are also aerosols which try to cool because of the, one is due to the aerosol radiation due to the scattering and reflection of the radiation. There are also aerosol cloud changes because aerosols can also facilitate cloud processes. And that's more uncertain. This is known as the direct radiative effect, and these are known as the indirect effects of the cloud and aerosols. But the net effect is a cooling with a large uncertainty. And so total, when you consider how much is the change in the radiation, because we have increased, all these changes have happened in all these greenhouse gases as well as the aerosols. So you can estimate how much the change in the radiative fluxes have happened at the top of the atmosphere. And so that turns out to be about, the net is about 2.72 relative to 2019 relative to 1750. So that much of energy we have added into the system. And what we also do in the, with these models is make future projections. And how these, there are different scenarios. I will not go into the 119 and 126, these are kind of low emission scenarios of the greenhouse gases and other anthropogenic drivers. And this is the SSP 245, this is a kind of the middle of the road. These are high emission scenarios, SSP 5 and SSP 3. And so there are models known as the integrated assessment models. So using that, they can design these different scenarios, and they can come out with the description of how these greenhouse gases and aerosols in different pathways. When I say SSP, these are known as shared socio-economic pathways. So under different pathways, how these, they have projections of how these greenhouse gases and aerosols will vary in the future, both spatially and temporally, and that is prescribed in the model, and these future projections are made. So right now we are typically following the kind of middle of the road, the SSP 245 kind of scenario. If we go with this, these are very, very low emission scenarios, very hard to achieve, and these are very high, this is not desirable at all. And this is the middle of the road, which is going business as usual. So if we go with this, we will still cross the 2 or 2.7 degrees by end of the 21st century. This is from the multiple models from the IPCC, unless we make very rapid reductions in the greenhouse gases in the coming decades. And so these are the typical, so we have the near term, that is 2021 to 40, this is 2041 to 60 is the midterm, and this is the long term. So I've just shown it for the SSP 245. So the very likely estimate in 2021 is about 1.2, about 1.5, the best estimate, but this we may cross much early. It's not 2021 to 2040. In the next few years, we are going to cross this. And the 2041 to 20 is 2 degrees. Again, it could be much sooner, the 2 degree best estimate, and long term is about 2.7. So clearly the warming is there, and it's affecting all the components. The sea level is, because of the warming of the ocean, there's thermal expansion. Also the glaciers and the ice sheets are melting, so they're adding more water. The sea level is rising, the cryosphere is melting. So, and so this is the observed warming that we see at per 1 degree warm global warming, and this is what is simulated by the models. You can see much of the warming is in the polar and the high latitudes, and the tropical and middle warming magnitude is relatively less. So with warming, we also see, this is in future when we are going to have 1.5 and 2 degrees and 4 degree warming, global warming levels, precipitation will increase in the future with increasing warming levels. So many of these areas in the mid-latitude are going to get wetter. And of course, for us, the Indian monsoon will also become wetter, because with increasing temperatures, there is more water holding capacity. So due to the increased water holding capacity, there will be more rainfall. That's what is projected. But many of the dry areas like the Mediterranean and some of the Saharan region and the subtropical regions, they are going to get drier. So it is because the circulation will rise over these wet regions and sink over these dry regions. They're called Hadley circulation. And so the wet gets wetter and the dry gets drier. And because of this increased dryness and as temperature increases, the soil moisture is also going to reduce in these areas. So they can have severe droughts, agricultural droughts. Yes, sure.
Can you please explain why this, for 1 degree global warming, like there is a distribution of like different region, polar region, warming more?
Yeah. So in the higher latitudes, basically it's covered by ice. So once the ice starts melting, so because of the ice you have a higher albedo. Albedo is so you reflect a lot. Now once you're going to exposing, the ice starts melting, there is more absorption. So the warming increases at the high latitudes. That is to a first order, but there are other atmospheric dynamics also. So to a first order, it is basically depends on the land surface. So the cryospheric regions they're going to absorb more heat as the ice starts melting. And so the temperature is going to increase. Yeah. So albedo means when you have the incoming solar radiation, a fraction of it is reflected. So if you have an ice-covered surface, that is going to reflect more radiation. Okay, but with warming, you also start melting and you are exposing. And if you have purely oceanic regions, the ocean will now start absorbing. Or if you have a land, it will absorb. And the question on aerosols, now these carbonaceous aerosols like black carbon, if they deposit on a white surface, they also start absorbing. That is one more, you can have this effect people are telling even the Himalayas, you have this black carbon that can also absorb the solar radiation and increase the melt and increase the temperature. So these are feedbacks that can happen. Yeah.
What goes into these models? Like we know that, I mean, you mentioned that atmospheric convection and so on, and various components absorbing. But we also know that ocean currents play a very important role. Is that also taken into account?
It is taken into account. I'll come to that in my, because these are fully coupled models. We are not just looking at the atmosphere.
Into the hydrodynamics?
Yes. We introduce, these are fully coupled ocean general circulation, atmospheric general circulation. Yeah. So one of the consequences of this temperature increase is that the saturation vapor pressure in the atmosphere, it has a dependence on the temperature dependence on saturation vapor pressure. So you can simply work out, this is what is known as the Clausius-Clapeyron equation. So if the temperature increases by 1 degree, the water vapor in the atmosphere can increase anywhere between 6 to 10%, okay? Typically about 7%. So a direct consequence of this water vapor increase is the frequency of heavy precipitation will increase. So heavy precipitation also globally, if you make an analysis, it increases typically by about 7% per degree warming, just like the water vapor increase. And so this is known as a thermodynamic effect. But there's a lot of dynamics when you're looking at extremes in the Indian monsoon region. It goes beyond this conventional Clausius-Clapeyron equation and the water vapor feedback. So with warming, what happens is the hot temperature extremes over land. If the mean increases by 1 degree or 1.5 degree, the tail of the distribution, they will become more frequent and also more intense. Intense heat waves, these are the 10-year extremes. They will keep increasing with warming. And also the heavy precipitation over land, with a 1% increase, it increases by, as I said, about 7%, 6.7%. So when you double it at a 2 degree warming, the land precipitation extremes will increase by 14%. These are very, very intense rainfall events or precipitation events, and they can lead to cause flooding and so on. So extreme temperature and precipitation is going to increase. So your question regarding when we talk about these weather and climate models, this is just a schematic. Normally what we do is we are looking at the equations of motions, the laws of thermodynamics to predict the changes in temperature, pressure, wind speed, wind direction, and humidity, water vapor in the atmosphere, and so on. And these are all highly coupled differential equations, partial differential equations. And obviously we cannot solve them using simple calculations, analytical calculations. So you have to resort to numerical calculations. So where we discretize them on a grid, on a sphere through finite differencing, or there are other techniques as well. And you do it as then you start with the initial condition, and with different time steps you keep integrating the model into the future. And obviously the time step is also going to depend on the resolution, the grid size. If you make the grid size smaller, your time step is also going to get smaller. And so typically we have millions of equations, tens of millions of equations. And now these models are also getting refined to coarser and, finer and finer grid. So the grid size is becoming smaller and resolution is increasing. Time step is getting smaller. So computationally it becomes intensive. And so this is just for the atmosphere. And so we have all the Navier-Stokes equation. You decide how the atmospheric general circulation is going to happen, how the winds are going to change, how the water vapor in the atmosphere, how the temperature profiles. So it's a three-dimensional structure and also time. And now you also, so when you couple with the ocean model, now you have to also take into account the physical processes inside the ocean, how the mixing is going to take place, how the downwelling is happening, how the upwelling, how cold water is coming from below, and so on. And so the atmosphere is coupled. The winds will drive the atmospheric temperatures, and the atmospheric temperatures gradients ocean temperature gradients in turn can affect the pressure gradients in the atmosphere. They are coupled to one another. You can get all these kind of feedback processes. And so now people are talking about going beyond, and they're talking about Earth system models, where we are looking at not just the atmosphere and the ocean, we are also looking at the coupling of the ice, the cryosphere, and we are also looking at changes in the atmospheric concentration of all these greenhouse gases and aerosols and other particulate matter, basically changes in the atmospheric composition, and what is happening to the changes, what is happening to the biosphere, what is happening to the vegetation cover, how it is affecting. So, and also the ground, we are also taking the land surface processes, because when rainfall happens, some of it goes into it enters the ocean, it also gets into the land surface, the groundwater, and so on. People are also looking at the changes in the ocean biogeochemistry, biogeochemical processes. So when we are really looking at the Earth system, we are looking at the rate of changes of all these changes about the physical, chemical, and biological mechanisms governing the rates of changes of different elements of the Earth system. And sun is the main driver. The energy from the sun is the main driver. And in fact, the IMD motto is the Aditya Jayate Vrishti. The sun makes the rainfall. It is a very, very powerful statement, which is very true. And this is the model that we developed from our IITM. This is the first climate model from India that participated in the IPCC, the Intergovernmental Panel on Climate Change, in the last assessment report. Now we are getting ready for the next IPCC report and this CMIP 7. So one of the important things is we should always ensure that before the model for the historical period and future projections are made, we should also ensure that the radiation balance in the atmosphere is achieved in the model. That means whatever incoming solar radiation is there and the outgoing radiation, there should be a net balance. And then you see, so the radiation balance is very, very important. And if you don't have that, there is some problem with your model. You have to fix it. And in fact, the first version of the model that we developed, somehow we realized that the ice in the Arctic was melting very fast. The temperatures were increasing. They were affecting the deep ocean circulation, because in the high latitudes, the temperatures are cold and also salinity is very high, high saline water. And so the water, because density is very high, it sinks in the high latitudes near the polar regions. And the warm waters from the tropics goes. So it's known as the thermohaline circulation. And it's important for the climates of America because of the Gulf Stream and Kuroshio. They take the warm waters northward. And so once the ice starts melting, the deep ocean circulation can change. People are projecting that with increased warming, the thermohaline circulation will weaken in the future. And and once that happens, you're obviously changing the sea surface temperature, your radiation balance will get affected. You are not, so in the first version of our model, we had a terrible radiation imbalance in the model, which we had to fix. Then we improved the distribution of ice in the model, the ocean circulation. This is the sea ice extent in the Arctic. It was terribly depleted in the first version, ESM1, especially during the summertime. And that we kind of improved substantially in the later version. And that led to improvements in the radiation balance of the model. And then once you have this radiatively balanced system, you can make these future projections and so on. Yeah. Yeah. So to a first order, the temperature of any planet, for example, Earth, is first order is determined by the energy that is coming into the system and the energy that is going out of the system. So if you do the energy, if you take these two, how much energy comes and energy, that will define the temperature of the planet. And of course, you have the greenhouse gases that is absorbing the infrared radiation. So it is imperative that all the models, climate models, are in radiative balance, because you are going to change the concentration of the CO2 when you make the future projections. So we know how much energy we have added and what would be the change in the temperature.
The change in the temperature is what you're trying to gauge, right? I mean,
Absolutely.
Gauge what is the net difference.
Absolutely.
You know what's coming in, but you don't know how much of it is going out.
Yeah, we know how much. Yeah, how much is going out has to be modeled.
Yes.
That depends on.
And so I don't understand how it can be input into your model.
It is not an input. So what we have to, what I'm saying is, to get what goes out of the model also depends on what processes are happening in the atmosphere. If there are problems, if there are biases in the model, you are not going to get it. So
you don't get the right temperature. It's not an input, but it's more that the modeling is not compensating.
exactly. So there could be, for example, now the first version I'm not showing you, this is the latest version, should get a typical imbalance. The top of the atmosphere net flux should be close to 0, incoming and outgoing. We had a bias about 0.8, which is still okay. Earlier, the first version, it was something like 8 watts per meter square, which was too much. So as I said in my beginning, the amount of energy that we have added is only about 3 watts per meter square, that due to the carbon dioxide and all the greenhouse gases so far. Okay. So your energy imbalance, when your model should be, you should have you cannot have an imbalance of 8 watts per meter square because it's going to be problematic. So typically it should be as close to 0 as possible. That's mine. Yeah.
I had a question. Yeah, so these are a highly coupled nonlinear equations. So how much do they depend on the initial condition? And how much does the, with slight change, how much do they divert, say, in a scale of 50 years or something like that? Yeah.
Yeah. So when you come to a weather prediction, that means we are typically looking at the weather for the next few days. It's an initial value problem. So it is very sensitive to your initial condition. Okay. So suppose there's a depression or low pressure in the Bay of Bengal, that should be there present in the initial condition so that you can predict. If it is not there, your forecast is going to go bad. But when you're looking at the very long time scale, it is mostly a boundary value problem. What is the change in the, I'm telling about 30 years or 40 years down the line, what is the change in the greenhouse gas concentration? That is going to mainly determine your climate. But intermediate, let us say next 5 to 10 years, there is some dependence on the initial condition as well as the boundary condition. So we are looking at, for example, a El Nino that is happening in the Pacific where the ocean warms up. So typically they can last for several seasons. And and I want to say, I want to predict whether there will be El Nino 3 years down the line. It also has a dependence on the initial condition. That is that problem. But typically when you look at climate change, it's a boundary force problem. Yeah.
Do I understand it correctly that at short time you have basically have a steady state in the system that basically defines the temperature, and at a long time still that steady state is the temperature is evolving slowly at that time.
Yeah.
Basically.
So when we say steady state, sorry, let me go here. This was what we typically do is before starting the model integration, we run the model for 500, 600 years when it comes to an equilibrium. And during this equilibrium, you can see this is the temperature should be of the entire planet. Of course, you can have some fluctuations, but it should be more or less steady, okay? And also your energy that is coming into the system should also be more or less fixed. It should not vary. There will be some small fluctuations, year-to-year fluctuations. Yeah. But on the whole, this is a 500-year integration, okay? Now we are preparing the next version. We have already run it for 1,000 years or so. So you have to get a steady state system, a radiatively balanced system. And once you achieve that, then you start adding, I will increase my carbon dioxide, I will increase my changes in the aerosol, land use change. See how it is going to affect your radiation and how it's going to affect the climate. That's the idea. And we also use this for making projections for the Indian region, and every country produces it. So US makes this national assessment report every few years. And for India, it was not there. So we came with a first assessment report of climate change over the Indian region. And I will be presenting this to your director, a copy of this publication, where we assessed it. So these are fully coupled models where we have the atmosphere, ocean. We looked at, these are the historical changes in the observation, how the model has projected. Also, these are the future projections from the model. We have looked at the Himalayan snow cover, the North Indian Ocean sea level rise, and so on. I'll not go into the details. So now that was the first part of my story. Now the question is, well, with climate change, the land is going to get warm, the troposphere will warm, and maybe the stratosphere cold, extreme rainfall will increase. But we are talking about a very unique region, the Indian monsoon, which is a very, very complex system, which is a very complex dynamical system, because you have the mighty Himalayas here, and then the Tibetan Plateau, the ocean, and during the summer monsoon time when the land gets heated up compared to the ocean, you have lower pressures to the north and high pressure to the south. So the pressure gradient sets up the wind from the high pressure to the low pressure, and this is the Coriolis effect. You have the winds as they turn here. You have the monsoon low-level jet. It is also known as the Somali jet. And here you will find that right at the equator, these mountains are there in the East Africa. They are known as the East African mountains, right on the equator. And they are important for producing this very strong divergence of the low-level jet. And this equatorial region itself, because the Coriolis parameter is 0 here, but the gradient, the latitudinal gradient of Coriolis parameter is very high. We call it as the beta, and that is very large. So the equatorial dynamics itself is a very, very interesting phenomena. I'm not going to those very interesting things we have to take into account. And then once these winds, as they traverse across the Arabian Sea and the Indian Ocean, there is evaporation. There's a lot of evaporation from the ocean surface. There's a huge amount of water vapor that is picked up by these winds. And when they interact, these moisture-laden winds interact with the Western Ghats and the Burmese mountain and the Himalayas, they form deep clouds. And so these deep clouds, when the water vapor is condensing to form clouds, it releases a huge amount of latent heat release, and which now from satellites we are able to estimate, and that can in turn affect the winds itself. If you are more heating, it depends on the vertical profile of heating, and they can in turn affect the circulation. And these winds also lead to upwelling in the oceanic region, because a lot of nutrients, when this divergence of the low-level winds happen, a lot of phytoplanktons and algae and nutrients, they come up to the surface. It's important for the ocean biogeochemistry, and you can monitor them from the chlorophyll from the satellite. So it's really a very complex dynamical system in this region. The question is, what will happen due to climate change? And so that was the idea, and so it involves multiple. So when we look at the monsoon, this is a picture I took from Rao, 1981. It's an old picture where they talk about Tibetan Plateau as a heat source. I will come to this. This is now being questioned by some new people whether you can call Tibetan Plateau as a heat source. I will come to that later on. And during the summer monsoon time, you have these cloud bands. One, as I said, the Somali low-level jet. This is very important. It picks up a lot of moisture. And you have the heavy rainfall along the Western Ghats, along the Northeast India or the Himalayan region, and also over central India, because there are many low-pressure systems, depressions they form. Here they move west-northwest, and they can also produce rainfall over the Northwest India and so on. And you have variabilities on the intra-seasonal time scale due to the slow movement of the cloud bands from the equator to the north. And you have also various weather systems like the lows and depressions, and clouds can be organized over very large areas. This is called as organized convection with smaller mesoscale systems. They produce abundant rainfall in this region. And of course, there is also monsoon extending into the East Asian region. We call it as the Meiyu. And in Japan, we have the Bayu frontal system. Of course, the mechanism is a little different there. So now question is, now with climate change already we are seeing many extremes. I'm not telling all that is because of the climate change. There is also a lot of natural variability. So we have to understand what are the causes, what are the teleconnections. Teleconnections means, I will show you, during some events like 2010 and 2014, there were very strong La Nina-like conditions in the Pacific, where the sea surface temperature was cool in the central and eastern Pacific. West Pacific was very warm. The entire circulation pattern over the India, the monsoon patterns were shifted westward. And they produced extreme rainfall over Pakistan and adjoining area, upper Indus Basin. I will come to that. And I will talk about the 2013 Uttarakhand event. This was a major heavy rainfall, led to flooding. And this led to about several thousands people died during this event. It was a big disaster. And 2010 Leh, this particular region, I thought I'll focus on the Ladakh region, which experienced a flash flood. This is one of the desert region, in fact. And Leh witnessed and this was a kind of mesoscale convective systems over the high terrain. And I'll also show some examples of the 2024 rainfall over Gujarat and Western India. And 2022, upper Indus Basin in some parts of Pakistan mainly, and also Northwest India, widespread and heavy rainfall. They were all associated with monsoon low pressure systems, depressions. That was one of the triggers, but they had other intricate feedbacks. I'll come to that. And this is the 2013 event where this region around Kedarnath and that region received massive amounts of rainfall. I'll show that. And this was the famous Shiva statue in Rishikesh. And this is the picture. This happened on 16 June 2013. And this was the situation on 2013. It was badly affected, the statue. Of course, now they've repaired, and now this is back. And we looked at this study by Vellore et al. Looked at many such cases in the Uttarakhand region of heavy rainfall events. And it turns out that during this time, a low pressure system went very quickly, because this is about early June, 16th, and monsoon typically would not have even reached. So this was a rapid onset of the monsoon during this period. A low pressure system went, and also this is a circulation pattern in the upper troposphere. So when I go back to my first slide, so in the low level, you have this kind of a westerly wind. Westerly means wind from the west. These are westerly winds, Somali jet. The upper level, if you take typically at 12, 13 kilometers, 15 kilometers above, you can see the winds are opposite. It's a easterly, because the air is kind of outflow. It's a divergent outflow. you will have what is known as the easterly jet and a big anticyclone, a high pressure region sitting in the upper troposphere. So once the convection, once this low pressure systems moves and the moist convection increases, this anticyclone becomes, up in the upper troposphere, becomes unstable. And around the same time, we also had a deep trough from the mid-latitude. It is extending right from the polar region into this region. So the convergence of this mid-latitude trough and this low-pressure monsoon system led to this, in this region over Uttarakhand, led to this massive rainfall. So this is another picture I can see. This is on 13 June, 15 June, 17 June. And this is the water vapor, 700 millibar precipitable water, humidity. You can see the low pressure system is moving, and this is on 15 June, and this is the mid-latitude trough that is coming here, and this is the region of Uttarakhand. And the moisture is basically the source of moisture is from the bay and also from the Arabian Sea that led to this massive rainfall. So there's a lot of internal dynamics to this when we want to look at the extremes, and many stations they are all located at very high elevations. The daily one day rainfall, 24-hour accumulated precipitation, were like 20 centimeters, 40 centimeters. It's a huge amount of rainfall, and they can lead to this massive flooding in these areas. And this was the Leh flash flood of 2021, and this was a paper by Rasmussen House. So this is actually located, Leh, this is a desert region in the Himalayas, Ladakh region, is a high altitude cold desert valley, 3,500 meters above sea level. But on this particular day, torrential rains delivered to this region by succession of mesoscale convective systems moving off the region triggered extensive flooding. So this was a lethal flood. So why I thought, because Hanley region in the Tibet is also of interest to RRI, and so this was a system. So basically what they argued using the satellite data and the in situ, so the land the Tibetan plateau gets heated up during the daytime due to the solar radiation, and some convective systems form, and slowly they migrate westward. This is a case of and at the same time, if you have the water vapor, the winds, if they transport the water vapor from the Bay of Bengal to that region, so these convective systems, that's a perfect trigger for this very deep convective events. And this is the conclusion. So this is the Tibetan plateau, this diurnally heated, because the land gets heated, convection develops, these convective cells form here, move westward, and then you have the moist flow from the bay, and then these big events can happen. Cloud bursts, massive. So, and so depressions become very important. That's the main point. And this is 2024, around 26th to 28th August, very badly affected many regions in Gujarat. And the system basically started somewhere in central India, moved westward, and it was and IMD could also predict it well. These were well captured in our models, and they had issued early warning. IMD issues red alert to many of these places. So the question is what happens, and this is the massive flooding that happened in that region in Western India. And these are the local things, but as I said, when you look at this is a recent paper we wrote about compound extremes. This is the 2020, the Pakistan and the Northwest India, in the upper Indus Basin, flooding that happened in 2022. Because there was intense pre-monsoon heating, and the glaciers also had melted at that time, and the soil was also moist, and we had a big La Nina. When I said when a La Nina in the Pacific, the trade winds were very strong, easterly trade winds. Sea surface temperature was very cool, and in the central and eastern Pacific, western Pacific was warm, so there was a gradient in the sea surface temperature. So there's a strong ocean atmosphere coupled interaction in this region. And so they can alter your circulation patterns, and there are also changes in the mid-latitude wave patterns. So at the same time, Europe was having a big heat wave. Likewise, in the China region, again there is in the Yangtze River Valley, there's a big heat wave. These are associated with what was known as Rossby wave patterns. I will not get into those dynamics. So they're all interconnected, and of course there was a low pressure system that went from the bay, from India, that goes into the Pakistan, that's a trigger. So, but many factors are coming into this system. We see the atmosphere, the ocean, the cryosphere. So when these heavy rainfall events happen, they all get compounded, and then that leads to this massive flooding. So now one of the question is, what will happen to the Indian monsoon circulation? How will it respond to global warming? Earlier, people thought that the thing is, this is the present. This is a simple schematic. This is the land, and this is the ocean. There is from the ocean to the land, there is flow of moisture, and clouds form, and there is a circulation. A deep overturning circulation can develop. So people argued that in the future, when the land warms faster compared to the ocean will also form, but this will warm faster. So there will be, due to the warming of the ocean, there will be more increase in the evaporation, there will be increased moisture. This will go to this region. But they said the circulation will become weaker. I will come to this. This is the main logic they use is the water vapor will increase at a very fast rate in the atmosphere. It will not rain so much according to this. So if typically it increases by about 10-15% of water vapor due to warming, but it will rain only 1% or 2%. So under that condition, the atmosphere will become stable. That means as you go up in the height, the upper layers will be warmer. You will have stable conditions. So this atmospheric stability increases and the circulation weakens. This was the hypothesis. And this was typically, this is the logic I will come to. This was by Held and Soden in 2006. So in the Pacific, you have this, what is known as the Walker circulation. As I showed here, typically you have the air rising in the Western Pacific, sinking in the Eastern Pacific, this big giant circulation known as the Walker circulation. And so with global warming, they Held and Soden argued that the Walker circulation will weaken. The logic is, if you see precipitation is basically is a product of the humidity and the vertical velocity. And when you look at the change in the precipitation and change in the water vapor and change in the vertical velocity, that is upward motions, water vapor increases by 7% per degree warming, whereas precipitation increases only 2%. So they argued that the circulation would weaken by 5%, upward motions will decrease. So the Walker circulation will weaken. This was the logic, and this is valid for closed domain. And many models also show that earlier they were arguing that the circulation, monsoon circulation would also weaken with climate change. But is it true? That's what we wanted to question. And the representation of the moist convective process in this, still there are challenges. And so we wanted to really focus on what is happening in the Himalayas and the Tibetan plateau, because the Himalaya is because it's one of the driver of the strongest monsoons. It's a source of 10 major Asian rivers, and it is the largest river of ice outside the polar regions. There's also a huge diversity in culture, tradition, languages, biodiversity hotspot. So this is from our climate change report. So this is a very, very interesting region, the Himalayas. And also we find that when we look at the temperature change over India and Himalaya, the Himalayas are warming at a much faster rate compared to the Indian region itself, the landmass. It's warming at a fast. So it's a very important critical issue. And this was a model that was proposed by in 2010. This was based on a paper by Booz and Kwang. I will come to that. So their logic is, as I told earlier, many people thought the Tibetan plateau is a heat source, that earlier school of thought. But now people are telling that the monsoon is basically driven by what is happening in the moist convective processes that is happening over the Indian region or the tropical region. And this is where the maximum subcloud entropies happen. And in the upper troposphere, you have a maximum tropospheric temperature change. And this is the Himalayas. Himalayas are basically blocking the mid-latitude cold air to come into the role of the Himalayas is to block the cold air, cold and dry air to come into the Indian region. And this is the Tibetan plateau. So they argued the Tibetan plateau doesn't really act as a heat source. So whatever dynamics is happening is all because of the moist convective processes that are happening, the representation of the clouds, how it condenses and how the precipitation is produced. That is what is going to determine this. And so they argue that received wisdom about the main driver of the South Asian monsoon comes into question with a report that tests the idea that the Himalayas, not the Tibetan plateau, are the essential topographic ingredient. It's the Himalaya, that's what they argued. And this basically was a Nature News and Views of the paper by Bose and Kwang, where they did experiments by studying they argued that the role of the topography, it's the Himalaya, not the Tibet, that is responsible for the monsoon. And Himalayas basically block Himalaya and Tibet, they are basically blocking the mid-latitude cold air to come towards this region. Otherwise, the monsoon would have kind of got diluted. And so if you did not have Tibet, you still have, with the model experiment, they still show that without the Tibet, but you have the Himalaya and the East Africa, you still can get the monsoon and rainfall and circulation. So now what we did in our experiment was we used this is a product work of my student, Ashwin Sagar. We have a global model, it's only atmospheric model, it's not coupled. We have a very high resolution zooming over the Indian region or South Asia, where the grid size is less than 35 kilometers. So we can resolve all these Hindu Kush Himalayas, the narrow Western Ghats, Burmese mountain and so on. And as you go away from this region, the resolution gets coarser. And interestingly, this model captures the observed distribution of the Western Ghat rainfall, also the rainfall over the Burmese mountains. There are some differences over central India, and you can see the very strong cross-equatorial flow, the Somali jet. The wind and precipitation are very nicely captured. There are differences though. I'll not go into the difference. Now we looked at two experiments. The SSP 245, there's the middle of the road. These projections are for the end of the 21st century. This is what I'm showing is 2081 to 2100, the 20-year period, minus the historical period. This is the historic, that is 1995 to 2014. And from the model, we make this, increase the carbon dioxide and all the other anthropogenic drivers in the model and make this projection. The SSP 245 GHG is another experiment where we only change the greenhouse gases. All others we don't change, and see what happens to the monsoon. We find a robust intensification of the precipitation for the Indian region as we due to the global warming, and also the Somali jet intensifies. So our result is counter to what Heldon showed an argument that the circulation will weaken. We are actually seeing a strengthening of the circulation in the future, and rainfall is projected to increase. And we also see that many places in the Western Pacific, we realize this appears due to the lack of a coupled model. This is just an atmospheric model, standalone atmospheric model. This we think it's due to the lack of coupling, but we realize this is one of the caveats of the model. But what we are finding is both the precipitation is increasing over a large area and the winds are strengthening. So what are the implications of that? It's not only in the lower level, even in the upper troposphere. So all the moist convective processes are getting stronger in this region with global warming. And in the upper troposphere, as I said, the tropical easterly jet is getting strong. These are the difference plots, by the way. SSP 245 minus HIST. So you can see a strengthening of the anticyclone in the upper troposphere. And also when you look at the sea level pressure, the sea level pressure intensifies that means these are low pressures. The low pressures are getting stronger. And this is important for all the depressions and all the activities of the monsoon synoptic systems. And one more thing, and this is we studied what is known as the heating, in that how much heating happens in the atmosphere due to the convection, moist convection. We find a tremendous increase in the heating over the land due to the condensation of water vapor. And this is the vertical profile. This is the SSP 245 and 245 GHG. There's a very strong vertical gradient of heating. So basically it will intensify the circulation patterns. And so the water vapor condensation becomes very dominant. And more importantly, having the East African mountains is very important, because for the Somali jet intensification, this is, by the way, with this grid that we are using, also has a very high resolution over the East African mountain region. And that is important to resolve these highlands over East Africa that are over the entire, A is the Mozambique channel, and F is basically your Saudi Arabia, and this is your E is your Ethiopian region. So these highlands are very important for generating the winds off the coast of Africa, and which can extend up to almost 3 kilometers. And then the jet actually accelerates. So resolving these mountains are very, very important for the monsoon. And this has been shown by several other studies like, so East African mountains, the heating, and so that's important for concentrating the Somali jet and the cross-equatorial flow. So what we find is with this high resolution model with further global warming, main point is precipitation increases substantially. Water vapor increases only slightly over the Indian region. Unlike the held and Soden where water vapor increased much more but precipitation did not increase. So in this scheme what we are finding is water vapor is very efficiently getting converted into rain. And so when that happens, basically your circulation also strengthens substantially and you have strong convective motions. And interestingly we find that these are for the low pressure systems that we tracked it, how many low pressure systems, depressions that form and go west northward. This is from the historical period, and this is the SSP 245 and SSP, this is with the warming. There's an increased genesis of the monsoon low pressure systems, and they can produce a substantial amount of rain. I'm sure many of them will be going towards the Himalayan region as well. So in summary, main point I want to suggest, highlight is heavy precipitation over the Indian region, Himalaya. It's an atmospheric dynamics. It involves circulation, the Tibetan monsoon circulation, Tibetan anti-cyclone. You can have also interactions with the extratropical circulation, the 2013 event, clouds and convection, and how these smaller mesoscale convective systems are organized. That's very important. Latent heat release, how the water vapor is condensing to form clouds. That's an important thing. Also, we have to look at teleconnections with the Pacific sea surface temperature gradients and how the water vapor is transported. These are all very integral when we want to study the monsoon heavy precipitation. We discussed many examples of the extremes. The Uttarakhand event, Upper Indus Basin event, Leh event of 2010, and also the JJ in summer monsoon extreme during 2022. So central to this is the low pressure systems from the Bay of Bengal. They are very critical for triggering these heavy rainfall events. And using a high resolution model, we looked at how, made just an experiment, how climate change can affect, how the global warming can affect the monsoon. And what we find is a robust strengthening of the summer monsoon circulation in the future. Somali jet will intensify, the upper tropospheric anticyclone, increased genesis of the low pressure systems, and moist convective events will intensify in the future. And this has big implications for heavy rainfall over the Indian region and Himalayas. So what does it mean? Now basically our models are already doing good, but localized extreme precipitation events, still we are having challenges. And so we need to enhance our early warning systems. So for this, as I said, for initial value problem, observations are crucial. Your initial conditions are important. We need the radars, the satellites, balloons, also the microwave radiometers for studying the vertical variations of the water vapor and temperature. And also it will help us understand how the regional climate has been behaving. And this has to be assimilated in the model for making predictions. And you need high resolution models with improved physics. Perhaps now newer techniques like AIML, artificial intelligence, machine learning techniques are coming. We could also bring them in. And more importantly, we have to link research to operations and applications. We have to strengthen basic research, there is no doubt, also education, capacity building. Also, more importantly, we have to coordinate with different other sectors like water, agriculture, transport, disaster management, defense, and so on. So that's the way for the theme for this today's talk, research to societal development. Thank you so much. Jai Hind.
Thank you, Dr. Krishnan. Open for a few questions. So the model predicts that there is a say 10% increase or 12% increase in total precipitation, but does it tell how it will be distributed? So say if it over 100 days, is it still like just increasing to 110 days, whether it's staying same or it's decreasing?
So we have not, because we can definitely look into it from the model and spatial pattern of this. I just took area average over a box. But maybe if I go back to my, this is the precipitation distribution spatially. So many areas you can see over the northwest and central India are getting stronger, also over the western Ghats. So these typically, you are also over the Himalayan region. Okay, so there is also a spatial, but we have not really looked at day by day. Perhaps we can look into, of course this is only a projection and we have to do many more realizations, I understand. But the key message is the moist convective process, as what Bose and Emmanuel, they are telling that in this region especially there's something called quasi-convective equilibrium. I'm not going into this. That was kind of highlighted in the schematic. Yeah. So the moist process in this region, the maximum subcloud entropies, how the clouds form due to the strengthening of the evaporation and the winds, the fluxes, evaporative fluxes, how the low level, how the clouds develop, how the entropy in the subcloud layer develops, and how the convection, it is through the convection, because of the convection, the temperature changes in the upper troposphere happen. That is what couples the low level and upper level. This is the idea of representing the moist convection through the quasi-convective equilibrium. This is very nicely captured in this particular model. How you treat convection, that's the key. And and also heavy rainfall, extreme precipitation is going to increase. I didn't mention that. It's not only the heating, because you can see a lot of water vapor condensing here, and also extreme rainfall will increase.
When we think about carbon dioxide increase, there is also some buffering mechanisms, like for example increase in plankton growth, and therefore like the oxygenation event which happened in the past. So, is there any idea of what is the rough timescales for these sort of feedback processes? Like for example, if I do a hypothetical pulse increase in the CO2 level, how does it relax to some steady state value? How much time does it take?
Yeah, so basically see my understanding is carbon dioxide is a very well mixed gas. The moment you release it, the kind of fossil fuel burning that is going on, some in gigatons, I think it's typically about 50 gigatons per year. That's the kind of carbon that we are adding into the atmosphere. It takes about less than a week to get well mixed in the atmosphere. Okay. And there are other mechanisms, they may be compensating, but the rate at which we are adding is humongous. And of course, the effect of the vegetation, and also the changes in the vegetation cover, Amazon is getting deforested. So obviously the absorption of potential to absorb the carbon dioxide is also getting reduced. So I really cannot, I don't know how much impact this will happen, the buffering effects. But clearly the way we are going, I think it's simply not sustainable. That's all I mean, which is not good, which is definitely not good.
So I've discussed, how do the long-term climate here? Okay.
Sorry.
Yeah. So how do the long-term climate models differ from, let's say, day-to-day weather forecast models? Like, do they have the same underlying equations, but you get like this initial value more often, or these underlying equations are also different?
Yeah. Now, if I take this particular model for the weather forecasting, it will do well. Now, for the day-to-day weather forecasting, my initial conditions are very important. And and how we are assimilating them into the model. That is the key, your data assimilation method and your observations that are going to be central. And I'm sure the model that, pretty confident, the models that they're very good for weather prediction. And one clear example is the weather prediction success is the tropical cyclone forecasting. Orissa 1999, the big super cyclone that hit, tens of thousands of people died. Now, 10,000 or something, I remember, close to that. Now that number has come down, and it is not one, whether it is Phylin or Hudhud. I mean, so the deaths are very, so tropical cyclone forecasting, that's a very clear success story in India, also elsewhere, globally. So this is all because of the improved observations, improved models, and also people are able to communicate, inform. The communication is also, and the state disaster risk management, state authorities are also responding. So preparedness, response, it's also happening. So cyclone is a very success story, but this heavy rainfall suddenly, like the Leh event, you are caught unprepared within a day. So cyclone forms over the ocean, so you have still time for this one. But the heavy rainfall event, we are still having challenges, and especially, there are examples 20 centimeters, 30 centimeters, even 50 centimeters in a day. And Mumbai, I remember the 2005 was close to a meter in a day. So those are extreme events, and catching. So models have problems there, getting those localized events. And probably we may have to, you cannot depend purely on these models, maybe other data-driven techniques like ML and other things, you'll have to bring them, but you need a lot of data for that. So I'm sure with more and more satellite data, in situ data, and these models improving, we'll be able to reach there. Yeah.
Sorry, I have one question. So you talked about the atmosphere and everything. Did not, I think, intentionally talk about the marine life and the water temperature in the ocean. Do you have any summary for that?
Yeah, the marine life, of course, I'm not also an expert on that. So the one thing is they have studied this ocean acidification, also that's also happening, one of the effects of the carbon dioxide increase. And it is affecting the coral reefs and so on. There is an assessment, detailed assessment and also with the polar region, the ice is melting. That's going to be a big problem for all these animals in the polar region. That's a big issue. Of course, I don't have and people have studied all these assessment changes. And there was some study, I remember, that the fish that used to come, the more Arabian Sea, they have kind of migrated more northwards. I don't know whether it's an effect of climate change, but some of the sardines which were more south, I think they have, looks like they have shifted more northwards. Definitely it seems to be affecting, but I don't know how much of it has been quantified. We don't know. And there are models for that as well.
So I guess we are already shooting over the time.
Maybe.
So if people are actually joining for lunch, maybe should have a broader discussion with him over lunch. Also, people are welcome to, hang around and ask him questions if he still has energy. Before we actually say final thank you to everyone, I would request our director, Professor Tarun Saradip, to hand over a memento for the speaker.
Thank you, sir. Thank you so much. Thank you so much, sir.
This is, we completed 75 years, so the Indian Post is gracious enough to.
Wow. Great, sir. Lovely. Yeah.
This is HA India agreed to work with us
Okay.
to highlight this research that came out over 75 years. So we selected some of them.
Wow. I deeply appreciate it. So I will just want to give you this. something in this. Maybe you can write.
Okay. Thank you, everyone, and thank you very much, Dr. Krishnan, for coming here and giving us this excellent overview of what's happening and whether we should be worried, and to put more effort in understanding the climate change and probably do some apply it in our day-to-day life. I know all this should be more involved in such kind of research. Okay, thank you very much.
Thank you so much.
Thank you. Thank you, everyone, for joining.
Oh, sorry. We can put it. Hello. Are you? Okay. Nice to meet you.
Half an hour.